Earlier, in earlier screencasts, I had discussed that in our everyday world, as we move around in cars and carts and bicycles and running and this and that, that accelerations are normally not constant. And so many of the problems we have in physics books, they are. And so if constant accelerations are rare and most change, like indicated in the graph below, what are some accelerations that are close to constant? So most of the time, for example, if you have a car and you push the accelerator halfway down and it generates a certain horsepower, the addition of energy is constant, as shown by this red dotted line segment on this graph. The kinetic energy of the car increases and increases and increases and increases. But if you look at the equation for kinetic energy, it's 1/2 mv squared. So the velocity is the square root of double the kinetic energy divided by the time. So the acceleration of a car increasing in speed is not constant. The car gets faster quite a bit at first, and then it gets somewhat faster, and then a little bit faster, and then a little bit faster, and then a slight amount faster as it goes. So the velocity does not increase linearly as the power is added linearly. So this is the normal scenario for most of us that don't fly in rocket ships. So what are some accelerations that are close to constant? Now, like we see in all the book questions and that are indicated graphically below, where the velocity would increase in amount linearly, and you get a slope here, and that slope would be a nice constant acceleration. But when you do that, though, kinetic energy of whatever your object is that's accelerating is getting exponentially greater, according to this equation. Now, this can happen, but it doesn't happen very often that we see in our everyday lives. So what are some accelerations like that are close to that? Well, okay. Can space rockets have that constant acceleration? Yes, they can, but how can that be different? We're going to discuss that. Can falling objects have constant accelerations? Well, yes and no. It's complicated. We're going to talk about that. And what about airplanes? Well, about that, that's a problem. Okay, back to the first one, our normal everyday lives. These explanations for these discrepancies mostly boil down to kinetic energy and momentum, as especially Newton's third law, relative motion, and frame of reference. We do know that impulse equals momentum. So force applied times the time over which it is applied, let's make that a constant force for the simplicity's sake, is equal to mass times the increase in velocity. So for a car tire pushing against the road, the car applies a force to the road pushes an equal force back. But don't forget, the car applies an impulse, the tire applies an impulse to the road, but the road applies an impulse back. If a land car is accelerating, imagine a world with only the car and the earth, and a car that's mass doesn't change, so it stays full of fuel. Let's keep the car's mass constant just to make it easy. As the car accelerates one way, if we look at this in a linear way, the earth very slightly accelerates the other way. And the faster the car is going, the less force it can push with, because it's in a higher gear. And for every meter moved forward, it pushes that force for less and less time as it gets faster and faster. So you can apply less and less impulse. So the momentum increases less and less each second if the power is applied evenly. As the car's motion progresses on a tire on a car, as its motion progresses, the imparted momentum is less and less, and acceleration decreases. Keep in mind the frame of reference is with the tires pushing against the surface of the earth. And that gives you this result here. For the power applied, kinetic energy increases linearly, but it can't do a constant acceleration. However, a rocket is a different scenario. For a space rocket, the same equation applies, and Newton's third law still applies, and all of physics still applies, but this time the rocket and exhaust gases are pushing on one another. So rockets do push on one thing, and that is the exhaust gases. As the exhaust gas is pushed this way with a force, an equal and opposite force pushes the rocket to the left. And the impulse that the rocket gains to the left is equal to the impulse the particles gain to the right. And the momentum the particles gain to the right is equal to the momentum the rocket gains to the left. All of this still applies. So the rocket exhaust gases are pushing off of the interior of the rocket engine here. So let's do the same thing and keep the rocket and the expended fuel mass, those two things constant. At least every second it's constant. Just to make it simple. Every second, the same mass of exhaust gases pushes off with the same force, speed, and momentum, and vice versa for the rocket. So the acceleration of the rocket is the same as it was the second before. It remains constant. At some point, when the rocket, this is interesting, at some point when the rocket gets going fast, the exhaust gases may come out really fast, but still be moving forward because the rocket is going so fast that as it spits exhaust gases out, the exhaust gases are still moving forward. The rocket is not tied to the frame of the reference of the Earth in the calculations. And what that means is the rocket can accelerate this way with a constant acceleration, and its kinetic energy is increasing exponentially. Because the rocket is always pushing off of the exhaust gases with it. That change in impulse is the same second to second to second. It doesn't decrease like it does with the wheel. Now, that lets us measure these different ways. For the car, we discuss power output in terms of horsepower or watts. Rockets, we discuss thrust in terms of newtons or impulse. In terms of newtons, or impulse in terms of newtons times seconds. These two indices don't directly convert from one to another, nor should they. Each applies to its own scenario, but not directly to the other. So those are the two extremes. Let's look at something else. Do falling objects have constant acceleration? Yes, they do, at least close to constant acceleration if you can meet these two conditions. One, air resistance isn't a factor. So we need to be in a vacuum here, or something pretty close to. And secondly, the object can't fall too far. If the object isn't falling too far, the force of gravity on the object stays pretty close to constant. Maybe close to 9.8 meters per second squared if you're talking about the surface of the Earth. If it falls a great distance, though, hundreds of kilometers, the force of gravity on that object increases as it is near the Earth, and that will make its acceleration increase. So let's look at it this way. If this is the force of gravity above the Earth, based on the Earth's radius, it actually falls over an inverse square function curve. Over large distances, gravity does this. At the surface of the Earth, it's pretty high, and it gets less and less and less as you go way off into space. So over large distance, gravity decreases significantly with altitude as an inverse square function. But if you've got these little red lines here and you're changing over a small distance of maybe tens or hundreds of meters, gravity is pretty much 9.8 meters per second on the surface of the Earth, and it's 9.8 meters per second squared. I should have said squared. Squared, 100 meters up, or 200 meters up. It doesn't change much, so that slope along that little section stays fairly constant. Now, let's take a look at what would happen in a satellite. Now, this comes from some previous work I've done. But if you are determining the potential energy in a satellite that's, let's say, 200 kilometers up, that's a pretty significant distance. You have to integrate that. The Earth's radius at the surface is 6.38 million meters, but 200 kilometers up, 6.58 million kilometers. And if you integrate this function, which describes the force of gravity above the surface of the Earth, you would end up with this integration. And you have to fall somewhere in a portion of this curve. And it's significant for that distance. That may be beyond what you're at now, but we've worked that sort of problem in here. Okay, so lastly, what about jet airplanes? Well, there are different myths. I'm going to leave that one to the experts. Propeller aircraft, and especially propeller aircraft driven by piston engines, are usually rated in horsepower or watts. Jet-propelled aircraft are usually rated by thrust. Jet aircraft get a lot of their thrust by accelerating exhaust gases aft, so Newton's third law and impulse equals momentum are a big part of describing their motion and acceleration. They're in their frame of reference once they're off the ground is the air that they're flying through. It's the fluid. But that argument about what's going on with airplanes and thrust and jets and propeller, that is far too complicated for this level. Let's just consider it's maybe somewhat of a blend between the two extremes of acceleration's either constant or kinetic energy is constant. And so what can even be happening there could be dependent on the velocity you have at the time. So let's leave that discussion to the fluid dynamics experts. It's interesting for us to talk about it, but we're not really prepared to deal with that scenario.